next slides, we will talk about lump parameter model for the catheter and sensor. Lump parameter model means that we will use some electric elements to model the performance of the catheter and sensor. We will use some electric element to explain the performance by some equivalent electric models. We don't have any real resistance, inductance, or capacitance inside the catheter, but the performance, the equivalent performance of the those parts are modeled by these electric elements. Okay. The liquid filled catheter sensor is a hydraulic system that can be best modeled by distributed parameters. A liquid catheter has inertial, remember it, inertial, frictional, and elastic properties represented by inertance, resistance, and compliance. It means that inertial properties are modeled by some inertance. Frictional properties are modeled by resistances, and elastic properties are modeled by some compliances, respectively. Similarly, the sensor has these same properties in addition to the compliance of the diaphragm. Analogous elements for hydraulic inertance, resistance, and compliance are inductance, resistance, and capacitance. Remember it. Capacitance for compliance. Resistance for resistance of the environment, and inductance for modeling the inertance of the environment. And as you can see in the model, we have a physical model here and equivalent parts, including some electric elements as electric analog model. For each part of a small part of a vessel, we can model this small part by a resistance, an inductance, and a capacitance. These three elements connected in this specific structure are for model only the simple part of this vessel. If we want to model more exact, we will use more segments. And if we don't want to model the system in detail, we can use we can model the system with a small number of segments. Okay, as you can see here, we have only 3 parts, 1, 2, 3, to model the all length of the catheter. But if, as I mentioned before, if we want to model the catheter in detail, we can use more than 3, 4, 5, 10 segments and 10 connected resistance, inductance, and capacitance part. The sensor has a chamber here, as you can see. The sensor has a chamber, and we use RS, LS, and CS to model this space, and the changing part of the sensor, the diaphragm, is modeled by another capacitance to model the changing compliance of the diaphragm. CD is for modeling the diaphragm, D refer to diaphragm, and is the variation of volume divided by the variation of the pressure. S here, RS, LS, CS refer to sensor, and C in RC, LC, and CC are referred to the catheter. Let us consider the details of these three elements, resistance, inductance, and capacitance of the model, and equivalent behavior between these elements, and also the relative behavior inside the flow, the fluid, and the flow of the fluid inside the catheter. We will use some equations to explain these behaviors, and we will talk about the equivalent characteristics between physical and also electrical behavior between these two the types of perspective. In this slide, we will talk about the resistance RC. First of all, we should mention the equivalent main parameters between these two spaces. We have two spaces in these slides. The first one is the fluidic and mechanic space, and the other space is the electric lamp, electric model space. As you know, we have an effort in electric space. We called it voltage. Voltage is the effort we apply the voltage on, for example, a resistance, and this effort leads to a current. And we have a simple equation here. I equals V divided by R. Or V equals I multiplied by I. I is the current or the flow of the electrons, and V is the effort or applied external field, electric field. In the equivalent space for mechanic space, fluidic mechanic space, the equivalent for voltage is pressure. Pressure is the effort and related current or similar role in fluidic mechanic space is the flow. Therefore, similar to the electric space, the resistance equals V divided by R, by I. We have a similar equation here. The resistance in the fluidic mechanic space, we have a simple equation here. Delta P like as V divided by F like I. Therefore, we can simply calculate the resistance in the catheter segments by knowing the applied pressure and the generated related current. And if we assume that we have a Poiseuille flow, a laminar Poiseuille flow, we can change this equation to another one. But before this equation, we can assume that we have a average velocity, and we have a known cross-section area. Therefore, because F is average velocity multiplied by the area, as you can see, area is here, and velocity we can replace the F by U multiplied by A, and we have a new equation here. Pressure divided by this product. In this equation, P is the pressure difference between two sides of the segment. F is the flow rate, U is the average velocity, and A is the cross-section area of the catheter. And if we assume that the equation is for the catheter, we can use the laminar or Poiseuille flow assumption, and therefore we have a specific equation for the resistance of the catheter segments. In this equation, L is the length of the catheter, R is the radius of the catheter, and eta, this is eta. Eta is the liquid viscosity. Like electric space, we can write the equation for the inductance of the lumped electric model based on some liquid inertance characteristics based on the delta P and also the derivation of F over T respect T, similar to the electric space. And also because we assume we have a simple velocity, average velocity, and a cross-section area, the derivation of a flow over T respect T will be the derivation of U, and this leads to average acceleration multiplied by A. As you can see, we replace the derivation of F respect T by A multiplied by A. Okay, and also we can simplify this equation to this one, and also we can rewrite the equation by this. In this equation, the inertance of the lamp electric model related to the density of the liquid, the length of the catheter, and also the radius of the catheter. In this in these equations, m is the mass, rho is the density of the liquid, and r is the radius, L is the length of the catheter. And remember that in your exam, some question may be from these, you have some questions from these equations. For example, if the density of the liquid inside the catheter increases, the inertance will be increases also. The length, if increases, the inertance will increase too. In this slide, we will talk about the compliance. Compliance is the acceptance of changing the volume of the chamber for determine a specific variation of pressure. For more explain, assume that we have two chambers, one with a flexible wall and the second one with a rigid wall. We have a rigid, thick wall and a flexible, non-rigid, thin wall. If we apply a same delta P for these two chamber, the first one, the volume of the first chamber will be increases more than the second one. The same pressure change and different changings in the volume of these two chambers. It means that the compliance of the first one is larger than the second one. because the delta V is small in compared to delta V of the second one. The variation of the volume divided by the variation of the pressure is the compliance. And also we can use the simple parameter, the inverse of the ED. ED is the volume modulus of elasticity of the sensor diaphragm. We can find the relationship between the input voltage, also VI, analogous to applied pressure, and the output voltage V out, analogous to pressure at the diaphragm, by using Kirchhoff's voltage law by this equation. Using the general form of a second order system, we can show that the natural undamped frequency omega n is this, and that the ratio of damping Kc is this. As you can see, the value of the parameters will affect the natural undamped frequency and damping ratio. Remember these equations. We have omega n and also Kc is it means that all the parameters will affect the value of the damping ratio. Damping ratio of the response of this system. We have a system here. Damping ratio is something like this. For example, we have a applied pulse like this, and the output voltage something like this, for example. And in this figure, the frequency is determined by these fluctuations, and damping ratio is related to this decreasing of the vibrations amplitude. Now we first will simplified the analogous circuit lumped electric model. We simplified this model, and after that we will consider the effects of the bubble inside the water. That complex electric model can be simplified to this one. Compliance of the sensor diaphragm is larger than of catheter or sensor cavity for bubble-free non-compliant catheter. Therefore, we can only use the CD here for modeling the compliance behavior of our system. And also the resistance and inertance of the catheter are larger than those of the sensor, because the catheter has longer length and a smaller diameter. Therefore, we will use only the resistance of the catheter instead of all the resistance inside our complete complex model. Now we have a simplified model when we can use only this model to simulate the performance and the behavior of the catheter. And for modeling the effect of the bubble, as you can see, we have shown the analogous circuit for catheter sensor system with a bubble in the catheter. We divide the catheter to two sides, distal and proximal parts. Distal and proximal parts of a catheter. We assume that we have a catheter here. Connected to the sensor here. And this is the proximal part and this is the distal part. And for bubble, we model the effects of the bubble with a simple capacitance, because the compliance of the system will be changed and the resistance and inertance of the environment will not change because of the bubble. And as you can see, we have two parts. This part is for modeling the, let me only show this part. This part is for distal and this part is for proximal, and this is for only the bubble part, and CD is for diaphragm compliance model. And also we can simplify the analogous circuit for catheter sensor with a bubble, assuming that LCD and RCD are negligible with respect to RC and LC. Therefore, we can remove the second part, the distal part, and we can only use the proximal here. And now, as you can see, after this assumption, the CB and CD are parallel together. And this is a so simple model to simulate the behavior of a sensor with a bubble. This slide